Welcome back, my dear children, to the part 2 of today's session from the chapter Oscillations. In this module, let us discuss about some systems executing SHM, oscillations due to a spring, and simple pendulum. So in the previous module itself, we had seen that the oscillation of a block of mass m, which is fixed to a wall by means of a spring, which is released after extending it, will start executing SHM. The restoring force acting on this mass m is given by f of x is equivalent to minus kx, where k is called the spring constant, and the system executes with an angular frequency equivalent to root of k by m, and time period t is equivalent to 2 pi into square root of m by k. The second example of systems executing simple harmonic motion is that of a simple pendulum. A simple pendulum is defined as an object that has a small mass, which is known as a pendulum bob, which is suspended by means of a wire having negligible mass. When the bob of the pendulum is displaced to one of the sides and then released, it starts executing oscillatory motion. The equilibrium position is shown by the dotted lines of the string. In the above image, one end of the bob of mass m is attached to a string of length L and another end to a rigid support executing simple harmonic motion. So we had seen that a simple pendulum consists of a mass m hanging from a string of length L and fixed at a point P. When displaced to an initial angle and released, it starts executing periodic and oscillatory motions. By applying Newton's second law for rotational systems, we know that torque tau is equivalent to I alpha, where alpha is the angular acceleration and I is the moment of inertia. Substituting for moment of inertia and angular acceleration alpha, we get tau is equivalent to m L square d square theta by dt square. It is equivalent to minus mg sin theta into L, where mg sin theta is the component which helps in producing the restoring torque. Rearranging the equation, we get d square theta by dt square plus g by L sin theta is equivalent to 0. We know that when angle theta is very small, sin theta can be approximated to theta. Hence, the above equation becomes d square theta by dt square plus g by L into theta is equivalent to 0. Comparing this equation with the equation for simple harmonic motion, we get omega is equivalent to root of g by L. Hence, the time period is given by t is equivalent to 2 pi into square root of L by g. Here, L is the length of the pendulum, which is the distance from the point of suspension up to the bob, up to the center of the bob, and g is the acceleration due to gravity. Hope you might have got an idea about the two systems executing simple harmonic motion. Thank you, dear students.